Welcome to this course on energy conversion and power generation. Energy is the foundation of modern civilization. From powering homes and industries to fueling transportation and communication systems, energy drives every sector of human activity. Yet, how we produce, convert, and consume energy has major implications for economics, sustainability, and the environment. This course will give you a deep understanding of the principles of energy conversion, the technologies of power generation, and the economic and environmental dimensions that shape energy use today. The course is divided into two main modules. Module 1, Fundamentals of Energy, Heat Transfer, Thermodynamics, and Fluid Mechanics. Module 2, Steam Power Plants, Gas Power Cycles, Combined Cycles, and Internal Combustion Engines. Module 1, Fundamentals of Energy, Heat Transfer, Thermodynamics, and Fluid Mechanics. 1.1 The World Energy Situation. Let us begin by looking at the global energy context. The demand for energy continues to rise as populations grow, industries expand, and technologies advance. Historically, the world relied heavily on fossil fuels, coal, oil, and natural gas. While these resources remain significant, concerns about depletion, rising costs, and climate change are forcing a transition toward renewable sources such as solar, wind, and hydropower. Forecasts show that even with strong growth in renewables, fossil fuels will remain a major part of the energy mix for decades. This creates a dual challenge, meeting rising demand while reducing environmental impact. 1.2 Energy Forecast and World Reserves. Energy forecasts estimate how long our reserves will last. Coal reserves are still abundant, but oil and natural gas have more limited lifespans. Advances in technology, such as hydraulic fracturing, deep-water drilling, and renewable energy storage, affect these predictions. At the same time, global policies on carbon reduction shape investment in energy infrastructure. Understanding reserves and forecasts is crucial for engineers, as they must design systems that are both efficient and adaptable to future changes. 1.3 Forms of energy and modes of conversion. Energy exists in many forms: mechanical, electrical, thermal, chemical, and nuclear. Conversion is the process of changing energy from one form to another. Examples include chemical energy in fuel converted to thermal energy in combustion. Thermal energy converted into mechanical work by turbines. Mechanical energy converted into electricity by generators. Every conversion involves efficiency limits and energy losses, often as heat. Understanding these limitations is key to designing better systems. 1.4 Power generation by turbomachinery. Turbomachinery refers to machines like turbines and compressors that convert energy between fluid flow and mechanical rotation. They are the backbone of modern power generation, especially in steam plants, gas turbines, and hydroelectric stations. For example, steam turbines convert the energy of high-pressure steam into mechanical rotation. Gas turbines use hot expanding gases to drive turbine blades. Water turbines harness the energy of falling water in hydroelectric stations. The efficiency of these machines directly affects the economics of power generation. 1.5 Economic and environmental aspects of energy use. Energy production and consumption always have economic and environmental consequences. Economics: the cost of building, operating, and maintaining power plants must be weighed against the price of electricity generated. Fuel costs, labor, maintenance, and infrastructure all play a role. Environment: fossil fuel plants emit greenhouse gases and pollutants. Hydropower affects ecosystems and communities. Even renewable technologies have environmental footprints, such as land use or material extraction. Thus, engineers must design systems that balance reliability, cost, and sustainability. 1.6 Electricity sector and load characteristics. Electricity demand varies with time, creating challenges for power generation. Load curve: a plot showing how electricity demand changes over a day. Peaks occur in the morning and evening, while valleys occur late at night. Annual load curve, a year-long record of demand, highlighting seasonal variations. Monotonous curve, a rearrangement of loads in decreasing order, used to estimate plant capacity requirements. Understanding these curves helps in planning plant operations and deciding which units run continuously and which serve peak demand. 1.7 Fundamentals of heat generation and transfer. Heat is central to energy conversion. The question is, how do we produce heat, and how does it transfer? Heat generation occurs mainly through combustion of fuels, nuclear reactions, or electrical resistance heating. Modes of heat transfer: conduction through solids, convection through fluids, and radiation through electromagnetic waves. Designing efficient boilers, furnaces, and engines requires mastery of these heat transfer principles. 1.8 Fundamentals of thermodynamics. Thermodynamics provides the foundation for energy conversion. First law: energy cannot be created or destroyed, only transformed. This law governs conservation of energy in processes. Second law: every real process involves energy losses due to irreversibility and entropy. It defines the limit of efficiency. Carnot cycle, a theoretical cycle that represents the maximum possible efficiency of a heat engine operating between two temperatures. Thermodynamics tells us that no system can be perfectly efficient, but it also guides us to maximize performance. 1.9 Basic principles of fluid mechanics. Fluid mechanics is essential for understanding turbines, compressors, and pipelines. Mass conservation: the amount of fluid entering a system must equal the amount leaving. Bernoulli's principle: in a steady flow, energy is conserved between pressure, velocity, and elevation. Compressible fluids: at high speeds or under high pressures, gases change density significantly, affecting design. Mastery of fluid mechanics allows engineers to predict and optimize flow in turbines, compressors, and boilers. Module 1 Summary. In this first module, we have built the foundations of energy conversion and power generation. We studied the world energy situation, reserves, and forecast. We explored forms of energy and their conversion, turbomachinery, economics and environment, load curves, fundamentals of heat transfer, thermodynamics, and fluid mechanics. These principles set the stage for our next module, where we will apply them to actual power generation technologies, steam power plants, gas cycles, combined cycles, and internal combustion engines.